Hi ladies and gents, I'm LimeyPlay. Thank you for coming to check out my video today. So the other day I was watching another globe versus flat earth debate over on Agree to Disagree. This was between Conspiracy Cats and Brandon Toy. I will leave links to their channels and the debate in the description. So, one of the things they were discussing was Coriolis. If you checked out any flat earth videos, and they all think that Coriolis doesn't exist, obviously because they think that we live on a flat stationary plane. Obviously that's not the case. We live on a spinning oblate spheroid. So one of the points that Brandon brought up was Coriolis effect and how if the Earth was rotating, obviously planes, like how come they don't have to correct for it. And then he also brought up sort of ballistic trajectories and how it seems that they don't really take Coriolis into account, or well, he even said that they sort of assume the other values when they're sort of taking test shots, and then they create a ballistic coefficient, which he thinks is the same as drag coefficient, to adjust the formula so that it works out how they want it. So he says that basically the math lacks any empirical proof and just doesn't work. So that intrigued me a lot. I thought I'd look into this all and educate the flat earthers. So first of all, one of the big things, they always say is, well, if the Earth's moving so fast, how come we can't feel it? And, anyone with half a brain should know that it's because of conservation of momentum. If it's something that you haven't heard about before or learned about in school, basically the conservation of momentum is because we are moving at that speed with the Earth so that we don't feel it. It's like, when you're in a car, you feel acceleration and deceleration, but once the car, the vehicle's traveling at a constant speed, to you it feels like you're not moving. Same thing with like being in a plane. Once they reach cruising speed, one of the flight attendants can pour you a cup of coffee. That coffee doesn't fly to the back of the plane because of how fast the plane is moving. It's all about like reference and sort of how or where you're looking at it from. If you get up to walk on a plane, obviously to you it feels like you're walking at your normal speed. But if we looked at it from the point of someone down, on Earth while you're up flying, you're in that plane. So technically you are also moving at, I don't know, I think it's like 900 kilometers per hour for a Boeing 747. So it's all about perspective, like where you're judging it from, because obviously it doesn't feel like you're walking that fast because you're in a closed system. And it's the same thing with the Earth, obviously, because we have the atmosphere, the gradient of the atmosphere, it being held by gravity. It creates a closed system, so we don't feel it. So let's look at Coriolis. So first we'll talk about, you got obviously, he was mentioning like ballistic coefficient, which he supposed was the same as drag coefficient. Drag coefficient is basically discussing it's the aerodynamics. It's how streamlined the bullet or projectile is. So because, like, obviously with a bullet, because it's streamlined, you've got different forces that act as resistance, obviously, which while it's in flight. Because the bullet's more streamlined, it is going to be acted on more dominantly by friction, as an outside acting force, to sort of slow it down. If it's something that's not as streamlined, well, let's say a lorry. Now think of the lorry for the moment as not being on the road. Just think of it as if it was traveling through the air, just because of the shape of it. This is just for the example. because of the shape, because it's not aerodynamic, it is going to be, it's going to be more affected by pressure over friction. Obviously, traveling on the road as it does in reality, this is where friction comes into play. But just shape-wise, if you threw a projectile, that was not streamlined at all. It's more pressure, air pressure, that is going to affect it. When it's streamlined and it's flying through the air, it's the friction of the air that would have more of an effect and get it to slow down. So that is drag coefficient. Now, because he also mentioned how Coriolis effect is not assigned a value, it's not calculated in shooting, and that even many of the other values are assumed. Saying again that the math needs empirical, or doesn't work empirically, and so. And then he supposed that what it is they assume these values, and then basically pull them out of thin air, and then they adjust the ballistic coefficient to alter the formula for the desired result. Now, there was a time, 19th century, where they did use the firing test method. This was obviously because, back then they didn't understand aerodynamics as well as we do now. They couldn't run simulations because they didn't have computers. So it really was, a case of sort of trial and error to try and learn how these things worked. Again, that was predominantly in the 19th century, which strangely enough seems to be where most flat earth research seems to come from. I think it's because there's no one left alive from there to argue the point against, really. So if we look at nowadays, there's a few quite a few methods on how to calculate all the trajectory and whatnot, and it doesn't need any assumption, and it can now be done before you ever have to fire the bullet or the missile or whatever the projectile is, because we understand aerodynamics and how it works. So going by the shape of it, they're able to work out by how streamlined an object is, and the shape of it. They can work out the drag coefficient. There's formulas for that, very complex. But they've been tried again, proven. It's just like every other big mathematical equation. They're not just made up; they are tested and tested, and to make sure they work from every different possible angle. And that's how we know that they're accurate. So they get the drag coefficient from that. To work out the ballistic coefficient, they're basically taking the mass of the round, or the projectile, and dividing that by the drag coefficient and the cross-section area of the bullet. So that is how they work out a ballistic coefficient. And each round, if they're all the same type of round, they all have the exact same ballistic coefficient, and that is a standard, that is an unchanging variable that can be plugged into the coefficient, into the formula, for that round. Obviously, if they then change the round, the ballistic coefficient can change. So that's that. And then you look at other variables as well. That obviously in this day and age we can measure extremely accurately wind speed, and direction, altitude, the angle of of firing, and velocity, which can be measured as well. And then obviously we can work out the momentum, which momentum is simply mass times velocity, which so we can work all of these variables out, or these answers out now very accurately. So then if we look into the Coriolis effect, so basically Coriolis effect is it just has to do with the spin of the earth and how it affects and it affects oceans, affects the atmosphere, and it affects flight paths of, of the ballistics and planes, etc. Obviously, planes, because they've got all of their equipment, to make sure that they're still flying level in relation to the Earth, so it is, because flat earthers will say that they'd have to constantly be dipping their nose down. Well, no, because gravity is uniformly pulling it towards the center, so it's going to shift itself quite well. And then plus, because of air turbulence and wind correction and all that, not with their equipment, obviously they're going to be making minor adjustments all the time. This is why you don't notice things like this. So when it comes to shooting, let's ignore, some of the variables. So we'll say that, it's a nice calm day. You're shooting on a low altitude, even sea level, or, not far from it. And, so you don't have to worry about those external variables for now. Coriolis will really start to be noticeable once you're shooting high ranges, especially like 1,000 yards or more. If you're in the northern hemisphere, because of the way Coriolis works, you've got the Earth is spinning from west to east. Okay, so as it spins and affects affects things, is basically, if you're in the northern hemisphere shooting, whether you're shooting facing north or south, as long as it's staying in the northern hemisphere, as it were, you're, without corrections, you would always shoot to the right of the target. And the opposite would be true for the southern hemisphere, where you would go to the left. And the reason this works is, so say if you're in the northern hemisphere, and let's say you're just above the equator and you're shooting aiming north. Now, because of the Earth's spin, around the equator is roughly 460 meters per second, which is just a little over 1,000 miles per hour. The higher up, you go, like the closer to the North Pole, it gets a smaller and smaller distance, when it's completing that full circle, because it's not as wide, obviously. So, those little bits are traveling slower to make their full rotation, whereas the wide part, obviously, you're traveling much faster, through space, as it were, to when you complete that rotation. So if you're in the northern hemisphere and you fire due north, okay, you're north of the equator, you shoot due north, is your bullet travels, because of the conservation of momentum as well, and because of because it's coming from a point that was spinning faster, the target isn't going to catch up, so you are going to go right of the target. And that's all because of the conservation of momentum. That bullet, even though you're shooting out of the gun, it already had an inertial reference frame, basically. Like when it was in the gun, it was already traveling with the Earth at at that great speed. Now, if we take it from the other way, if you're in the North Pole and you decide to shoot shoot south, because you are now moving slower, your target is going to going to beat you basically through space. And so again, you're going to miss to the right of the target because you're moving slower and you won't catch up with it. So that's why obviously they have to make adjustments. Now that right there on its own proves the Coriolis effect. To prove it even more, and that we're on a spinning ball, because obviously if, on the globe there's the curve, which they don't believe, flat obviously don't believe in that. If you again, perfect conditions, let's say you're at the equator and you've got a target set up 1,000 yards east and the same again west. When you fire, basically if you shoot to the west, because of Earth's rotation, and you're going to have a good, I think you might have a good like 6-7 seconds or so. I think it's quite a bit of time from when you shoot to when you hit the target anyway. So, but the Earth is rotating and because of the curve, that target is going to come up higher because the bullet is traveling in the air, so it's basically going in a straight line, whilst being affected by other forces, but for the majority is going straight. So as that target comes up over the curve, or just because of the slight curve, it's not a huge curve at 1,000 yards, it's going to come up and your bullets are going to hit lower. Okay, obviously, furthers might just say that that's because of gravity and, bringing it down so you hit lower. But if you then shoot a target 1,000 yards to the east, what is going to happen is, because of the Earth, is rotating to the east, that target is going away from you. So if you're using, the exact same rifle, on a nice flat table, it's all leveled out, and, without changing the adjustments, you're shooting for the center of that target again. Because that target is going away from you and it's going down the curve, you're going to hit high. Now, there is no way to replicate that experiment on a flat, motionless plane. It is just not possible. This experiment definitively proves that we're on a sphere, and it proves the Coriolis effect. We are in fact spinning. So I'll play a clip now. Wonderful video of this gentleman on Gunworks doing this exact experiment, and you guys can see it for yourself.
Now, real quick, let's kind of just explain the Coriolis effect in layman's terms. The Coriolis effect is the effect that when the bullet leaves the barrel of the gun, it is actually leaving the surface of the earth. So as the bullet leaves the barrel of the gun, the earth is still rotating, and the bullet is not rotating with the earth. So the earth will actually rotate out from underneath of the bullet while it is in flight. So as the earth rotates, it actually rotates from the west to the east. So what that's going to do to our targets is if you're shooting west, your target's going to rotate up and towards us, which is going to cause the bullets to hit lower. And if you're facing east, the target's going to be dropping and slightly moving away, which is going to cause the hits to be higher. Now, to show you guys just how much effect there's going to be, we're going to put on a little shooting demonstration here. I've got targets east or west and east of us, exactly 1,000 yards in each direction. So what we're going to do to prove this Coriolis effect on our rifle here is we're going to shoot it out to 1,000 to the west, and we're going to shoot it to 1,000 to the east, and we're going to measure the difference in those group centers, and hopefully it's going to show you guys that this kind of error can lead to bigger errors in your drop data. All right, got 3 hits on the steel down there. We're gonna switch directions, switch the bents over, and we're gonna shoot east now. All right, we've made it down to our target that we shot at the west. This is our west target here. And as you can see, they've all dropped in quite low. We've got 8 inches from center to the center of the group. Which is a little lower than we expected, but we were dealing with some pretty stiff mirage. So we got a nice little group here. We're gonna pack up this target and head down to our target that we shot to the east, and we'll compare the 2 groups and show you the difference of just switching directions. That's all we did. We switched from west to east. All right, we've made it down to our target on the east target now, and as you can see, they're not quite too high. We've got about 3 inches, maybe 3.5 to the center of the group above bullseye. So if we compare this to our other target, we're 3 inches high here, we're 8 inches low there. That's 11 inches, just over a minute of difference between just shooting from the west to the east.
All right. So yeah, as you see, Coriolis effect does have to be taken into account because we do live on a spinning ball. Brandon, I hope you get to see this video, just so just so that you can see how that does work. There isn't any math out there that needs to be empirically proved, because it has already, yeah, I hope you guys enjoyed the video. I will be doing some more on, like on the conservation of momentum and momentum in general. Just because I don't know, just going into looking through all this trigonometry and stuff, I found it very interesting, and so I will be doing some videos on that, and I'll prepare some slides so we can go through it all and actually look into all the variables. And I'll probably do one on the shooting as well, because there is a lot of different stuff to cover with that. So I'll knock something up and create some examples and show how, especially at the long ranges, you have to account for everything, wind speed, angle, and again, the spin of the earth. So until then, I'm LimeyPlay. Thanks again for coming to watch me today, and I'll see you next time.